Hello guys, welcome again. This is our third podcast on packed bed column and probably it will be last on the packed bed. And again we have Vikas Yadav with us and my name is Dhananjay Tiwari. We are from VNIT third year chemical engineering students. So we have already seen that in a packed bed how to calculate friction factor and heat transfer coefficient. But mass transfer is also a very important phenomenon in chemical engineering and many chemical industries. So I have questions regarding that. So the very first question, what is the mass transfer coefficient in a packed bed column and why is it important in process design?
So basically, the mass transfer coefficient quantifies the rate at which the species move from one phase to another phase. That is, example, gas to liquid phase. So, in a packed bed column, it's essential for designing absorption, as we have discussed that absorption, distillation, and chemical reactors, as it determines how efficiently components are transferred and separated. Okay, a high mass transfer coefficient indicates that a better performance and smaller column sizes for the same separation duty. So basically, just if the mass transfer rate is high, so our design parameters can be very small. So if the basically mass transfer coefficient is the only thing from which we are designing the reactors. If our the mass transfer coefficient is less, so we have to design a tall vessel, very tall reactors. But the mass transfer coefficient is high, so we can reduce the size and get the same rate from very small reactor.
So it greatly affects the cost of the plant.
Cost of the plant, cost of the reactor, designing parameters.
So yes, it is means it is very important for the economy of the industry. So as we have seen previously that there are many key factors that influence the heat transfer coefficient, friction factor. Are there any key factors that influence mass transfer coefficient, and if they are, what are they?
So basically, the key parameters are similar as of that we had discussed in earlier problems.
Heat transfer coefficient.
The heat transfer and friction coefficient. So basically, the first one is the flow rate, as we had discussed that flow rate is a designing parameter that we cannot have such a great velocity of fluid or something we are putting inside on cannot be have very slow flow rate, so we have to adjust it to an optimum level. Secondly, the packing type and size, as we have discussed, like packing material, shape, size, word fraction plays a very much huge role in that packed bed. And fluid properties we discussed, like viscosity, diffusivity, all in all. Temperature and pressure are also important. Like temperature we had discussed for that heat transfer coefficient, and pressure will be here for that mass transfer coefficient. So basically, and the wettability and distribution. Wettability, that we have learned that the fluid will be coming in contact with the outer shell of that
bed should be completely wetted
by the fluid which are flowing inside the packed bed. So these are the various parameters that is required in the packed bed column.
Okay. So again, my third question will be like in heat transfer. How can we measure the mass transfer coefficient? Is it through we conduct experiments and obtain those mass transfer coefficient, or we find it by using some correlations? How do we find it?
So basically, we can find the mass transfer coefficient by both the ways. Can be estimated by physically, that is experimentally, and can be theoretically determined. For experimentally determining the mass transfer coefficient, there are some techniques such as tracer techniques. Measuring the concentration profile along the column, you can measure the concentration profile along the column. So you can get that step or pulse input method. You can give the response of step response or something. You can get the experimental result at the mass transfer coefficient. And empirical relations are also there, for which you can determine the mass transfer coefficient by theoretically or by solving this on a paper. So basically, there are formula called Sherwood number equals to A into Reynolds number to the power B into Schmidt number to the power C. A, B and C are the constant. It varies for different processes. So here you can put the various values of that Sherwood number, Reynolds number and Schmidt number. You can easily get the mass transfer coefficient by that.
Is there also like we have seen in heat transfer, there was Kolban factor.
Chilpan Kolban.
So is it also there in mass transfer?
Yes, yes. You can use these are also analogies. From these numbers, you can get the other parameters like H, K, DAB.
Okay.
So from there, you can estimate that mass transfer coefficient.
Okay. So, like we are suppose we are measuring through the experiments, we are finding out the mass transfer coefficient. So, what are the challenges that there can be in finding out or measuring the mass transfer coefficients in a packed bed column?
So if you are doing it experimentally, it been a quite tough than theoretically, because in that column, the water or that whatever we are fluid is coming from inside, there might be fluid maldistribution, not evenly distribution of the fluid. So that can be a lead to inaccurate rate measurements.
Because ideally we consider that the fluid is covering entire area.
100% wettability. Secondly, wall effects in channeling. Because of these void spaces, there must be some channels are formed. So the fluid is flowing through the channels, not everywhere inside that packing material, but they are coming from the channels. So most of the space are as it is. There is no fluid flowing through that.
So the main purpose of our packed bed phase there is the channeling is there.
Channeling is not required, but is occurs due to some errors. Third one is scaling up. Lab results and industry results are not very much accurate. So you cannot estimate that doing in such a small packed bed column and directly correlate to the industrial level. You cannot. There is some difference also. Then non-ideal flow patterns, because mostly we consider, for simplicity, we take calculation for laminar flows and all. But in industry, we had seen that turbulent and transition phases are also there. So for this, that's are the major difficulties we are facing estimating and experimentally.
In laboratory, we may do the experiments, but since we are studying this transport phenomena subject, we definitely will be using only correlations only. So to understand how we can find mass transfer coefficient, and let us do a numerical and understand it in a better way, so that it will be easy for you to grasp the concept.
So we will be doing an experiment. You will easily know how to calculate the mass transfer coefficient. So let's solve the problem.
Okay.
Thank you.
So in our previous two videos, we have seen how we can calculate friction factor and heat transfer coefficient in a packed bed column. In today's numerical, we are going to see how to calculate mass transfer coefficient in a packed bed column. So let's write the question. So you might have noted down the question. Now let's read out the question. Pure water at 26.1 degrees Celsius flows at the rate of 5.514 into 10 to the power minus 7 meter cube per second. So volumetric flow rate is given. Capital V volumetric flow rate is given through a packed bed of benzoic acid spheres the packing material of our packed bed is benzoic acid spheres, and this packed bed is having a diameter of 6.375 mm. Okay, the total surface area of the spheres in the bed is 0.01198 meter square. This is the total surface area of the spheres, means the surface area of the packing material, and the void fraction is 0.436. Epsilon is given as 0.436. The tower diameter is 0.0667 meter. This is the diameter of the tower, and this was the diameter of the particles. So diameter of the tower is this, means diameter of our packed bed. The solubility of benzoic acid in water is 2.948 into 10 to the power minus 2 kilomole per meter cube. So this is the solubility of benzoic acid in water, means concentration of the interface of solid, means benzoic acid, and water. And now what we have to find? Mass transfer coefficient Kc and exit concentration of tower Ca2. So let's draw a diagram so you can understand better. Assume this is our packed bed of spherical particles. These are benzoic acid particles. Okay. Yes. And water is sent here. The concentration of water will be 0. There is no benzoic acid initially, and the concentration at the exit of tower Ca2, which we have to find later in this question. The diameter is given, diameter of the bed is now we will see the solution of this question. Now solving any of the packed bed question, the very first step is always to calculate Reynolds number, which we have done in our previous two questions also. So here also, firstly we will calculate Reynolds number, particle Reynolds number. This is given by dp rho v by mu. This is the diameter of the particle. So everything is given. Diameter of the particle is given, which is 0.00635. Its density is given, and now the velocity is not given. Instead, it is given that volumetric flow rate. So we can divide the volumetric flow rate by cross section area of the packed bed. Then we'll get the velocity of the water. So volumetric flow rate was given 5.514 into 10 to the power minus 7 divided by the cross sectional area. So here the diameter will be of tube or our packed column, 0.0667 square divided by the viscosity was given at 26.1 degrees Celsius. If you put all the values correctly into the calculator, you will get the Reynolds number as 1.15. So let's write this value of Reynolds number into one corner. Reynolds number came out to be 1.15. Now in calculating heat transfer in a packed bed, we have written the formula of Chiltern-Colburn factor for heat transfer. Here we will write the Chiltern-Colburn factor for mass transfer. So its formula is given as Colburn factor for mass transfer is equal to 1.09 divided by void fraction to the Reynolds number minus 0.67 is equals to mass transfer coefficient divided by velocity, not volumetric flow rate, multiplied by split number की power 0.67. Now this Kc we have to find, velocity we have calculated, volumetric flow rate divided by area. Reynolds number we have got 1.15. Epsilon value is given. The only thing which is unknown is Schmidt number. So the formula of Schmidt number you might remember is mu upon rho AB. This Schmidt number we are finding at 26.1 degrees Celsius. Now this viscosity is given at 26.1 degrees Celsius. Density is also given. The only thing that we don't know is this DAB at 26.1 degrees Celsius. But instead the value of DAB at 25 degrees Celsius is given. So we'll use this terminology which says that the diffusivity is directly proportional to temperature and inversely proportional to the viscosity. So DAB at 26.1 degrees Celsius divided by DAB at 25 degrees Celsius is equals to 26.1 degrees Celsius, which will be into Kelvin we have to convert. So that will be 299.1. Mu is given at 26.1 degrees Celsius, which is 0.8718 into 10 to the power minus 3. Mu at 25 degrees Celsius is given as 0.8920 into 10 to the power minus 3, and the 25 degrees Celsius into Kelvin is 298 Kelvin. This is given into the question. So we will send into right hand side and we get the diffusivity value at 26.1 degrees Celsius, which will be 1.245 into 10 to the power minus 9. So now everything is known. The viscosity at 26.1 degrees Celsius is known. This density is known, and DAB we have just calculated. So we'll put all this value into this formula. Then we'll get this Schmidt number value as now let's write all these values into one corner. That number came out to be 702.56. Okay. So now this equation was 1.09 divided by epsilon Reynolds number. Now in here we know all the values. Void fraction we know. Reynolds number we just calculated 1.15. This Kc is unknown, which we have to find out. Velocity we have calculated, volumetric flow rate divided by cross sectional area. Schmidt number value is 702.56. So without a delay, let's calculate the Kc value. Kc is equals to 1.09 into Reynolds number value was 1.15 power minus 67. This velocity which we have calculated divided by Schmidt number was 102.56 power 0.67. Epsilon was given as what was the epsilon value? 0.436. Velocity was 1.578 into 10 to the power minus 4. Put all these values correctly into the calculator, you will get the value of Kc as 4.448 to 10 to the power minus 6 meters square per second. This is the value of Kc that you should get, and if you are not getting this value, then probably there is a calculation mistake. So let's move to our second part of the question, which was concentration at the exit of the tower. This Kc value will be useful for us. So write it at one of the corner. So from Fick's law, we know that mass flux multiplied by area gives the mass rate, which is A Kc into Ckl minus Ckl This Ca1 is the concentration of water at the entry of the tower. This was the Ca1, which was 0 because there was no benzoic acid present. Ca2 at the exit of the tower we have to calculate. So that we will take as it is. CAI, you will be wondering what CAI is. CAI is actually the concentration of the interface of benzoic acid and water, which was given as solubility. You might have noticed that CAI was CAI was 2.943. Have to check once. Into 10 to the power minus 2 kilomole per second. Now, this is actually a log mean driving force because the concentration is constantly changing inside this packed bed. So we are instead in place of directly using the driving force, we are using log mean driving force. So this comes from Fick's law actually. And if you will do the material balance, you will get another expression of mass flux, which is Ca2 and Ca1. Here we are directly using the driving force, which is the Ca2 minus Ca1. This V is volumetric flow rate, already given into the question. Now this is the equation 1. This is equation 2. If we equate both these equations, then we'll get the value of Ca2 because everything else is given into the question. Area, this area was given, which was total surface area, which is 0.01198 meters square. This was given already in the question. So let's put all these values. So equating previous two equations, we'll get Kc is equals to volumetric flow rate by area, which is velocity of the water. You can directly use the value Ca2 minus Ca1. Ca1 we know, which is 0. Ca1 is 0. Ca2 we have to calculate, divided by that log mean driving force. I'm not writing that expression. I hope you may have found that value of the log mean driving force. And AC we have already calculated, so we can calculate the exit hour concentration. So I'm directly writing the answer so that you can match. 2.842 kilomole per meter cube. This is the exit concentration that you should get. So with this or this topic of estimating mass transfer coefficient in a packed bed column ends. Thank you very much.